The purpose of today's activity is to find the speed of sound in air. We're going to use an air column to do that, the whole idea of resonance in an air column to do that. The basic apparatus that you're going to use is what you see up on the board here right now, and what I am holding in my hand here right now, slightly bigger version of it. There is a plastic tube that we're going to put water in. Inside that plastic tube with water in it, we're going to put another smaller plastic tube, a PVC tube. This PVC tube has numbers on it. We can measure distance, it's centimeters on this. We're going to pour water in this. And then as we pour water in it almost to the top, okay, almost to the top, we're going to hit a tuning fork of a very particular frequency. Okay? Maybe 264 hertz, let's say. Okay? Got a tuning fork of 264 hertz. We're going to hold it above the plastic tube here. And then we're going to adjust the length of the plastic tube. Last week when we were going over this whole resonance thing, this whole standing wave thing, I drank water out of my cup or out of my bottle, blew across the top of it, produced a certain frequency. Drank more water, produced a different frequency. Drank more water, produced a different frequency. I changed the length of that air column by drinking water. Today we're going to change the length of the air column in a much easier way. All we have to do is pull up or push down this middle tube. As we do that, the length of the air column between the top of that tube and where the water is, which is where the sound reflects off of, right, and produces a standing wave, changes in length. So as I pull it up, the air column becomes longer. As I let it fall down, then the air column becomes shorter. Now, how do I know what the length of the air column actually is? Well, that's what the centimeters are on the side of that PVC tube in the middle for. Okay, that's what it's measured in centimeters for on the side of that. As we pull it up, and we see the water level is at, let's say, this point right here. Okay, this point right here on that PVC tube in the middle. If it says 61 centimeters on the PVC tube where the water level is, then the length of that air column is 61 centimeters. Easy, right? Put the tuning fork over it, adjust this. Okay, we're going to get a certain length of air column to where the water boundary is, the water-air boundary is. Now, how do you know what length to make it? Well, you're going to hear resonance taking place. You hit the tuning fork, you're going to hear a sound. In this case, you're going to hear 264 hertz. You're going to hold it over top. You're going to continue to hear 264 hertz. But as you lengthen the air column, at some point, you're going to hear 264 hertz, but it's going to become really loud. Does that make sense? So it's 264 hertz, fairly quiet from the tuning fork. We hit a tuning fork the other day. You guys know that it's a fairly quiet sound. But as you hold it over top here, quiet, 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 quiet. As we lengthen it, at some point, it's going to become loud. That's when it's resonating. Okay, that's when we found the first standing wave of that air column. Record the length of that. Record the length at which you hear that loud sound. The point at which you hear that loud sound is this, the first harmonic of that air column. Does that make sense? Then you're going to keep lengthening it. The loud sound is going to disappear. It's going to become fairly quiet again. Quiet, 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 quiet as you lengthen the air column. And then again, at some point, it's going to get loud. That's your third harmonic. Measure the length of that one. Record it. Your third harmonic is going to look something like this. Not quite like that. There we go. More like that. As the diagrams last week showed us. Record the frequency of the tuning fork you're going to use. Record the length of the air column when you heard the first loud sound. Record the length of the air column when you heard the second loud sound. That make sense? Record it in a table that looks something like this. Tuning fork number 1, frequency. You can use whatever tuning fork you want to use. Okay, temperature of the room. I measured it earlier. It's 21 degrees Celsius. The first resonance level, record the length at which you heard it. The second resonance level, record the length at which you heard it. Easy enough. It's like shampoo. Repeat as desired. Rinse, lather, repeat. What are we going to do? Rinse, lather, and repeat for a second tuning fork. A tuning fork with a different frequency, which should, of course, make you get different lengths of air column, giving you the first standing wave and then the second standing wave. Whatever lengths of air columns you get, record them. So we got two different lengths for two different tuning forks. Once you've got the frequency for two different tuning forks and then the length of the air columns that produce the first two standing waves for each of those frequencies, then you're going to do a little bit of an analysis. Now, the good news is for this activity, the analysis is given to you in the form of questions. There's no procedure to write down for this. There's no graphing to do for this one. Hey, there's no conclusion to do for this one. All you're going to do is answer the questions that are given to you at the end. The first one, and again, I'll give you a chance in a minute to copy this. Calculate the speed of sound using the equation. Should be 332 plus 0.6 times t. So get the speed of sound. We know the temperature of the air is 20 degrees Celsius. Get the speed of sound. Then you want to find the value of the speed of sound using the first harmonic and the third harmonic. Why not the second harmonic? Why do we not use the equation for the second harmonic there? Because it's a closed air column and there is no second harmonic, right? So it's the first harmonic and the third harmonic. You guys remember the first harmonic looks like this. The length of the air column is 1/4 lambda. Lambda is 4L. F is equal to V over lambda. F is equal to V over 4L, but we want to solve for V here. So it becomes 4 times L times F. Get the equation for the first harmonic. Now the third harmonic is 3 times the value of the first harmonic for speed. That means that F3 will be 3 times V over 4L. That means that V will be 4 times L times F, right? The 4L goes up by multiplying. The 3 goes down by dividing. The third harmonic will look like this. Get the speed for the first harmonic and the third harmonic for the first frequency, then do the same for the second frequency. Get the average speed. The average speed is found by adding those 4 speeds up, dividing by 4. And finally, you're going to get what we call a percent difference. I don't know if you've done this in chemistry before at this point or not. The percent difference is the actual minus the theoretical over the theoretical times 100. We're trying to find out how far off we are from what we should get. Now, question number 1 gives us the theoretical speed of sound. Okay, right over here. Whatever we get here, that's the theoretical speed of sound. So put that in right here. Whatever value you get, put it in right there. Whatever value you just got from question number 3, that's the actual speed of sound, what it really worked out to be. Take that value, subtract the 2, divide it by the theoretical, and then times it by 100. Ideally, you're going to end up with a number that's less than 10%. In other words, whatever the speed of sound really should be, somewhere in the 340 meters per second range, you're going to get somewhere really close to that. 330 meters per second, 328 meters per second, 351 meters per second, something like that.